Hello everyone, it's Justine Habib from Mr. Ismail High School. In this video, I'm gonna explain rotational kinetic energy. You can study that from Survey Engineering, Chapter 10, Section 7. So let's get started. First of all, a definition for kinetic energy, which is the energy associated with the body motion. So when I say rotational kinetic energy, I mean the one that is involved when an object is rotating about a fixed axis. Notice that the center of the object is still stationary. See the difference. When I have a rotational kinetic energy case, object is moving in a circular path, no translation is involved. On the other hand, if I have a translational kinetic energy case, the object is traveling for a d distance, its center is traveling. Okay? So let's take a close look about what is rotational kinetic energy. Here I have an object which is rotating about a fixed z-axis with an angular velocity equal to omega, and I have that particle which is about r distant from the axis of rotation, and it is moving with a vi or v tangential. So if I want to calculate the rotational kinetic energy for that particle, it will equal to half mvt squared. But that is for one particle. So for the whole system, of course, I'm gonna put a summation sign for the rule. So this sign means that the rotational kinetic energy for the whole system equal to the sum for the individual for the particles. Okay, and we know that Vt equal to omega r. According to that, Vt square is equal to omega square r square. Make a substitution, and we have half summation mr square omega square. And of course, you can recognize mr square as moment of inertia. So we commonly refer to kinetic energy or rotational kinetic energy equal to half I omega square. Let's take a small example about that. So here I have two masses with m capital about the x-axis and other two masses of m small about the y-axis. Distance as shown here as a and b. And it tells you to calculate the moment of inertia and the rotational kinetic energy about the y-axis. So for the y-axis, notice that you will only consider the masses on the x-axis, and the masses on the y-axis will cancel. And why is that? Because they have no motion about the axis. Okay, so here we only calculate the masses on the x-axis, which leaves us to have a moment of inertia about the y-axis as equal to ma square plus ma square, which is the masses on the x-axis and their distance from the axis of rotation, which leaves us to finally have 2ma square. And for rotational kinetic energy about that axis or the y-axis is equal to half moment of inertia about that axis omega square. Same idea if it asks you about the rotational kinetic energy about the x-axis, you will cancel the masses on the x-axis and you only consider the one on the y-axis. But if it asks you about the rotational kinetic energy on the y-axis, about the z-axis, which is perpendicular to the whole plane, you will consider all the masses with no cancellation, which leaves us to 2ma squared plus 2mp squared. That is the moment of inertia about the z-axis. For the rotational kinetic energy about the z-axis will equal to, of course, if I multiply that by half, it will cancel the 2. So leaves us with ma squared plus mp squared all in a bracket times omega squared. So we can conclude from that example that is the moment of inertia, and therefore the rotational kinetic energy is associated with the axis of rotation. It depends on the axis of rotation. And that is all for this video.